Okay. I want to open this session about optical networking. The first thing I want to say is that please remember that mobile phones should not make any noise in this meeting, because that would help everybody's concentration, I think. Furthermore, there are slides, general slides, but I don't know what exactly the contents is of these general slides because we can't present them here. But at least what I know is that be really in time for the dinner this night. I think you will hear it from other people also, but it's essential that you be in time. I don't think that the doors will be closed after, but really be there on time. Okay, to start on optical networking, steps towards true optical networking. That's the first session about, in the sequence of two. We first start with the things which have been done at a quite high level, really looking at optical networking most of the time. So in this case, we are looking at pure optical networking, and so not the let's say the PR term of optical networking that you still are using 1 gigabit or 10 gigabit or SDH links, but really at switching colors and that kind of stuff. So I think it is not really something which will be usable in the coming 1, 2 or 3 years in the networks. Perhaps it is, but it would be nice, of course. But it's more to give everybody a flavor of what's happening in this environment, which could be very important for the views of national research networks and the research in this environment. So first we will talk about, Didier Colle will say something about projects done in the European Commission in this environment. Then Reijs will talk about optical packet switched WDM networks. And after that, then we'll see more on optical packet switching from Lars Dietman. So 3 things which are perhaps not really practical at this moment, but I think they are very important for the future and so on. So I want now to give Didier Colle the floor to say something about the IST projects being run now at this moment. Didier.
Okay, thank you for the introduction. So as mentioned, I will present you some projects of the 5th framework that run or have run in the past. So now the Optimist Project, or Optical Technologies in Motion for the IST program, is a thematic network map that clusters IST projects working in the optical domain at the network level, subsystem and component level, so quite a broad scala of projects. The goal of the Optimist project is to facilitate exchange of information, dissemination of results by organizing workshops, having a website, a quarterly newsletter, and so on. We also use in the Optimist project those results from those projects to build a roadmap. So just one quick word on the roadmap. We heard already about ambient intelligence, and it is seen as a crucial part in this, that the intelligent optical networks will, in the end, interconnect all the parts of the ambient intelligence environment. So data storage resources, computing resources, routing resources, whatever, making them available to the end user which has a wireless access, for example, with this PDA. Now, important in this ambient intelligence environment where everything is very trivial to use is the development of a universal optical plug. Just as you have your power supply plug, you plug it in the wall and it works. Okay, so but let's go more into technical details, and let's start with high bitrate projects. Now, how can we achieve high bit rates? Well, first of all, nowadays we are using already wavelength division multiplexing, what means that you have different light sources at different wavelengths. Each of them is modulated with another information stream, and then those signals are multiplexed onto the same fiber. At the other side of the fiber, you separate again the channels. from this WDM signal. Now at the other side we have optical time division multiplexing, where you have, for example, a generator of very short pulses, and you send those pulses to different modulators to allow modulating different information streams, and then those signals are delayed relative to each other so that they become interleaved, and that if you combine them, you get a much higher bitrate signal. So you do time division multiplexing in an all optical way. At the receiver side, you have then to select again for each pulse to which receiver you have to send this pulse, and this is one of the more complex operations in OTDM. Now, what bitrates can we achieve over a fiber? Well, nowadays it's already in the order of tens of terabits per second, mainly by using double DM. OTDM suffers from important dispersion impairments and so on, so that you cannot achieve the same bit rates by only using OTDM. Now, okay, you have a quite broad spectrum, but anyway, if you want to use this efficiently, you have to be able to modulate as much bits per second per hertz, and state-of-the-art is already able to achieve modulation of 1.6 bits per second per hertz, but the problem now is still that you can send such a signal only over quite a short distance. Those experiments here with 1.6 bits per second per hertz is for 80 kilometers, and so a challenge for the future research is to enhance this capacity distance product. Okay, so this was about point-to-point links, where you have already quite a lot of phenomena, attenuation, dispersion. You have also nonlinear effects and other physical impairments that become quite important when you have wavelength channels with a very high bitrate, typically in the case of OTDM. Now, if we go to really optical networking, so where you have network nodes switching signals all optically, then you are cascading filters and other devices, and so you are accumulating the impairments that come from those devices. Another problem is that if you have signals coming from different links and joining on one link, they may be on different power level, for example, and when you switch signals, you can notice transient effects and so on. So developing all optical high bitrate networks is quite challenging because you have many issues to take into account. So now let's go to the IST project, and what we have done is we classify them in: do you have directly electrical signals multiplexed by means of double DM, or do you have an intermediate OTDM layer? And another classification is at the right. Do they have an all-optical ad-drop multiplexer to demonstrate limited networking functionality? Let's start just with the point-to-point project. Atlas demonstrated the transport of 4 times 40 gigabit per second wavelength channels by means of double DM over 500 kilometer, and after 200 kilometer you have an all optical wavelength converter, because they see this as a very important component in future networks, because for example you need such component to resolve wavelength contention problems. So they have used a dispersion map that has been optimized for the second wavelength channel, and so for the other wavelength channels, they need at the receiver side dedicated compensators to rephrase the signal so that they can properly be received. Here are just some results in terms of bit error rate measured at the beginning, simulating a back-to-back connection, after the optical wavelength converter, after 400 kilometers, and then after the full 500 kilometers. And you see that over that distance, the bit error rate increased. But if the power is sufficiently high of the signals, the bit error rate can be kept acceptably low. Okay, now the top rate project, how does that differ from the Atlas project? Well, it differs in the sense that you now have an intermediate OTDM layer. So you have your 4 times 40 gigabit per second signals that you multiplex into a wavelength channel of 160 gigabit per second. And then they also have the possibility to multiplex those high bitrate wavelength channels, so multiple of such 160 gigabit per wavelength channels. So, but the main difference with the Atlas project is the intermediate OTDM layer. Let's go then to the project having limited networking functionality. The Meteor project aims at demonstrating a metropolitan terabit optical ring, and so it makes use of a double DM ring that multiplexes 40 gigabit per second wavelength channels, and the all optical drop multiplexers here are then able to add and drop wavelength channels from these double DM signal on the ring. Whereas when we go to the Fashion project, we have also an all optical drop multiplexer, but there they aim at demonstrating dropping 10 or 40 gigabit per second signals from a 160 gigabit per second wavelength channel. So here the drop multiplexer is not based on double DM but on OTDM. Okay, so let's leave the high bitrate project and go more into the networking related projects. The first distinction that can be made are those networks circuit switched, so switching wavelength channels, for example, or wavebands or whatever, or do they switch all optically bursts or individual packets? Another distinction are those networks static or dynamic networks that are able to provision in a flexible way caps between nodes where the user really needs them at that particular moment in time. Such flexible networks typically features a distributed control plane. And finally, we have projects working in the long haul area, some in the metro area, and then finally others in the access area. I will start with the optical packet switching, optical burst switching projects. Stolas is one of them, and the architecture considered in the Stolas project makes use of optical packets that have the payload intensity modulated on a wavelength channel, and the header of the packet is then orthogonally modulated as an FSK signal. So in the end, what you get is a two-level labeling hierarchy. You have just the color of your signal, what can be interpreted as a label, red or blue, can mean different things, so that's a label. And then you have the FSK labels that form another hierarchy. So the demonstrator is not yet there, but just to give you a flavor of one of the theoretical studies, different services are, traffic for different services are taken and hopefully for a realistic forecast, and then the performance of the network architecture is measured taking into account the architecture of the nodes, how the optical bursts are assembled, because typically you will not switch individual IP packets, but you will have a burst of packets within one optical burst. Then what we see is, first of all, that in terms of amount of lost traffic, that this is quite high, a loss ratio of above 10⁻⁉. I think this is quite high. Probably the reason for this is that in the optical domain, there's not memory available as we have the RAMs in the electronic domain. So if you want to do buffering, then you can use fiber delay lines to create limited buffers. But this is not sufficient to get acceptable loss ratios. Another thing, what we see is that if we assemble longer bursts, then the loss ratio will go down. Another project is the IST David project, and this project is based on a broadcast and select switch architecture, whereas the Stolas project is based on an array waveguide grating, which is kind of a lambda router. If you have an incoming signal, the signal is then routed to a port depending on the wavelength of the incoming signal. But about the David project, I hope Lars will tell much more on this in the last presentation in this session. Then going from the more technology-driven to the more software-driven projects, we have the Lion project, where automatic switched optical networks have been studied. And one pillar is more theoretical studies that have been carried out, coming up with some guidelines for the evolution towards ASINs, how to optimize such networks and so on. Also, it is investigated what ASINs can bring in terms of survivability. And finally, what is the gain that you can have by having statistical multiplexing of switch connection instead of having just permanent connections, and that in the context of network planning. So, but we have also in that project a detailed study of the functional architecture of such a control plane. So you have different components in such a control plane. And what is particularly interesting in the Line project is that the management of such networks has been studied, and an information model has been developed for such networks, because now it's not sufficient anymore to manage the transport or data plane, but you have also to manage, for example, the control plane itself. And this result, this resulted then in a test bed where you have two different domains managed by different management systems. And so what has been demonstrated is, first of all, the setup and tear down of soft permanent connections from one domain to the other domain. Soft permanent means that one of the management systems triggers the setup of this connection, and then the actual routing and signaling is handled by the control plane. Another type of study done in this testbed is on multi-layer survivability. Now, Wingmom is also a project on network management. Mainly, it deals with inter-domain management. And so, what the setup is of the Wingmom approach is to have a single access point for the service level management to the different domains. And so, that single access point, that inter-domain management system, makes then abstraction of the different domains and of the technologies used in those domains. Then to finish up, there are also projects on access. HEAnet is on a gigapon architecture, and Harmonics is based on a multi-wavelength access network that is reconfigurable. Reconfigurable means that capacity can be allocated to other users when they really need it. And to conclude, I want to encourage you to visit our website, where you will find more information on all those projects, also contact information. So if you have questions, you can ask them directly to the project. You can also subscribe to our quarterly newsletter, and you can find information on, for example, our workshops and so on. Thank you for your attention.
Thank you. Thanks, Didier, for the explanation of all the projects running at this moment. I think it gave a good overview of all the ins and outs of these projects, and even gave a nice overview of where you have to look for. Are there questions? There's time for a few questions. Okay, Renaud. The microphone at the end. Wait a moment. Can you wait for the question?
Didier, maybe it's a complicated question, but you described all these kind of projects that investigated various ways of doing optical transmission or metro networks. Did you also consider how the telecommunications market or the ISP market is evolving, and that some of the concepts you described, like Lion, that looks very much like ATM on optics, are they still relevant, or shouldn't you look at sort of what the advanced communities like these people here are doing, and how sort of networking is evolving, and that this could be a valuable input to sort of how you structure your research and come up with solutions that are easily taken up by this community?
Well, I think first of all, for sure, projects like the Lion projects, there is quite a lot of interest of that industry, and also from this community here, I think there is some interest to really do research on such things. So I think there are opportunities for it.
Okay. Is there one more question? Okay, I think there's always time to ask questions afterwards. Thanks very much again, Didier, for this talk. Okay, I want to go to the next one then. It's also looking at optical packet switching in DWDM networks. It will be presented by Reijs Neabati, and he's currently working for the Essex University on photonic networks. And I think it's a little bit, it's quite interesting to know what we can do, perhaps already now, or perhaps in the near future. The floor is yours, Reijs.
Thank you.